lowercase letter, uppercase letter G for graphs. And I have been reserving it to denote groups. And groups come out very often in this. So we cannot really use it for graphs. And on the other hand, this is one reason. The second reason is that the graphs are spaces now. So it is natural to denote it by X, Y, Z. So now we have the GBA group. We didn't say it is finite. You have to really, if it is finite, the way of assuming finite, I would have written finite as well. Of course, finite is allowed. Let GBA group, quiz question. Does any group have a generating set? Generating set means it's a set of elements. It's a subset of the group, so that if you keep multiplying elements in here and taking the inverse and multiplying, you get all the elements of the group. Cyclic group has a generating set consisting of one element. I'm asking, does any group must, if G is a group, then does G have a generating set necessarily?
Yes.
Yes. What? Give me an example. The whole group generates itself. So this means that there exists this one, and then you try to reduce elements, and then you come to a smallest one. So we are taking a generating set S. So every group has a generating set, no problem. Okay, so we will get the S here generating set. Oh, there's a beautiful problem here for group theory, which I always, especially when I'm on the ground, I want to ask questions immediately. For any given group, if the minimum generating set has only one element, we have cyclic group, it's all determined. Although there are also questions about cyclic groups. If it is any group, even if it's finite group, how is there a good algorithm to find the smallest generating set? If you work on this question, you can produce a paper. It's an algorithm question. So let me just give you any finite group. A finite group of 1024 elements. Give me an algorithm which quickly finds the minimum generating set. It's a computational problem. Even if you are given a cyclic group of large order, let us say the order is about 700 digits. You know why I'm taking 700 digits? Do you know?
Yes.
It's because of the cryptography, right? So if you have a cyclic group of a 700 digit order is 10 to the 700. Can you quickly find its generating element? Because cyclic group, we know that it has only one generator.
Yeah.
It has a generating set consisting of only one element. Can you quickly find it for me? If it is not given to you, we only know the elements of the group, order of the group, and we know it's cyclic. What is the generating element? Let us not go to group theory. We are now going to matrix space theory and graphs. That is definitely a question, and of course, some people think that everything is known about abelian groups, and therefore everything is known about cyclic groups. But I don't really agree with that, because there are open questions in number theory which relies on one. So let G be a group and S be a generating set, which exists, no problem. And suppose that Dr. Farooq is also not here, sorry. So nobody except you can correct me if I make a mistake. So generating set, and suppose that. So we can finish the lecture even earlier, so it's fine. Suppose that identity element is not in it, and one more, S is closed under inverse. So inverse of S is X. We take this. Now we define a graph, which is called K graph. Cayley graph. If you haven't known this yet, this is a good place to know it. This is the Cayley graph because it is determined by x, t and x. X equal to x, g, x is given by the specification. It's an undirected graph given by the specification. This is a computer marked word, given the spec of the computer, the specification. The specification is a vertex set is G. H set. We said already that for undirected graphs, the graph can be, the mapping which is the graph can be completely determined by the vertex set and edge set. And you can actually equate the space with the union of the two. That we said already. This is given by edges are all pairs of distinct elements. So we call it xy. Xy are elements, of course, because vertex set is G. Xy are group elements. And xy inverse belongs to x. This is the definition of a Cayley graph. A question. Still a quiz question. Why do we need to assume that S is a generating set, number one? Why are we supposing two conditions? Identity element is not in it and inverse closed. You need to answer me.
We didn't include included to avoid loops.
Sorry? Yes.
To avoid loops.
Identity is not included because loops, we didn't,
Yes.
it is not, we didn't want to include
Yes.
loops. Loops doesn't give anything for matrix spaces.
And I think the condition manages equal to S will keep the graph connected.
Yes.
But I'm not sure.
So the connectivity is guaranteed by the, because when the matrix space is not connected, we can
Yeah.
study it component by component.
Yeah.
So of course you can have matrix spaces which are not connected. But we are considering connected. This implies that if the graph X is connected. Did you study graph theory before? Yes, good. Connected. And this implies that there is no loop. We are not imposing like Professor Trump, President Trump. We are not imposing this tariff on everybody. We are doing this no loops for the only reason that we are studying matrix spaces. And if there is a loop means vertex point is just to itself. That doesn't give change to the distances. Because if we're looking at distance from here to there, this is 2. This is not counted anyway. That is 1 there, but if we don't add that one, but that will be 3 and it is not minimum. So this reason is for giving us reason to assume this. And when you are studying graph theory, this was introduced to you by Paul, and without any explanation. You need to give 2, 3 good reasons that every condition we are using is we are using. What is inverse closed? That condition. Why do we have S inverse S?
Direction does not matter.
Undirected. Undirected. If it is not closed on the inverse, you will get a directed graph. So you're getting this is actually a XY, round bracket. In order to drop that round bracket, we don't want to go back and say we don't include the diagonal and we forget the order and we don't need to go that far. We just do it here now by assuming that S inverse is S. Which means if there's any this in S, then its inverse is also in S, which means it's going, the edges have no direction. Edge has no direction. So that is one reason for each of these, and then we get it together. Now,
S is a subgroup?
sorry?
S is a subgroup of G.
S is not a subgroup. It's a generating set. It doesn't have to be a subgroup. If it is also closed under multiplication, yes, it is a
Professor?
subgroup. Yes.
A few days ago, we studied a graph for Gaussian integers. I think that was also a Cayley graph.
Yes.
Where the generating set were unit elements.
Yes.
The sets was magnitude of
Yes,
6.
that is exactly. And in that case, we have a set G, the group G is infinite.
Yeah.
It's an additive group of the Gaussian integers, which is a ring. Ring means the additive group is abelian. Very good, thank you. Before we throw examples, there must be some conceptual minor things we need to get out. What other things are there? Okay, let's do the example, and then we will start seeing with the question, and then I will come back and ask. Example. Let us take a group of order 6. What group comes to your mind quickly? The cyclic group of order 6, right? In the notation of Z sub 6. Even this will surprise you because you might not have seen this before. Of course, this is a cyclic group. There is generating set with only one element in it. And if that one element inverse is not in it, then it doesn't satisfy the third condition. And you can't include 0 in it. 0 is the additive identity element. So if it is 2 elements, then they have to be inverse to each other because of this condition, right? You have to consider all of this later. Now I'm going to include 3 elements. If you include 3 elements, what observation can you give on those 3 elements? What does the third condition give you? 1 is not in there. There are 3 elements, A, B, C, let us say, in the generating set. Of course, a cyclic group also has generating set of 3 elements. So, if inverse of A is B, and inverse of B is then necessarily A, but then C is 7. So, if it is odd number of elements in S, then there must be an involution. Which means in this case, if we are going to say take 3 elements in S, we have to have 3 units. This element, 0, 1, 2, 3. 3 has 3 is an involution. 3 plus 3 is 0. So let us take, we always include this. Let us assume that S has 3 elements. And we're going to take 3 elements, 2 of which are inverse to each other. The other one is 3 all the time. So one case, S is equal to, this is the first case, S is equal to 1, 3, 5. 1 inverse is 5, 5 inverse is, negative of 1 is 5, negative of 5 is 1. Negative of 3 is 3. What do we get? I'm not going to even label the graph. This has 6 vertices because the group has 6 elements in it. So now, set of vertices G, so 6 vertices. I'm not going to even label, and without labeling you can get it actually. Only you need to know that one of them is 0. Let us say this is 0. Then what does 1 and 5 give? If it is turning, this is 1, 2, 3, 4, 5, then it is going this 1 goes all the way this way, adding 1. And if you go this way, you get the same edge if you use 5. What if you use 3? 3 is 0 plus 3 is 3. 1 plus 3 is 4. 2 plus 3 is 5. We saw this graph before, right? Yesterday, or on Monday. This is K33. Let us reprove it. If you have 3 vertices which are hollow, and then we say this is not hollow, then we can actually give these two not hollow. And you see that red and hollow are all adjacent, but no red is adjacent to red, no hollow is adjacent to hollow, because that one is not adjacent to these two. There is no edge there. Similarly for red. And then every red is adjacent to all 3 white. So this is cases. You recognize it. This is our old friend which is coming out as a member of new family. Just got born, and then we don't need to give names because he has his name already. Now let us take another one. So 3 must be there. What are the other 2 elements? 3 must be there. You can take 2
and 4.
4. And we will see whether we have the same graph coming out. This is one possibility. This might give the same graph, but in which case where we have some nice, interesting phenomenon. Let us do it here. Now this is 0, 1, 2, 3, 4, 5. Adding 2 means jump over 1 vertex, right? Adding this 2. So the namely that this is 2. So y is obtained by adding 2. So we go there, there, there. For that one we go there, there, there. But 3 is still there, so it has to have those edges as well. Is this graph known? We saw this before? A quiz question. For graph theory students, this has to be examined. We're not probably going to examine in this one. Is this graph known one? We have seen this before, or not? Let me draw another graph here, so that you can probably try to see. Is this isomorphic to this one? Clever people with good visual ability can quickly tell me it is isomorphic, but the most stupid way of doing this is that you give labels 0, 1, 2, 3, 4, 5, and then you give labels 0, 1, 2, 3, 4, 5 in this, so that the adjacency is exactly the same. But it is easier than that, because you see, we draw a trilateral there first, draw another trilateral there first, and then 2 trilaterals connected by edges. But whichever way you connect for, it is trilateral, it's not 4. It will be exactly going the corresponding vertices. So this is isomorphic to this graph. And this graph is also known from Monday, because what it is now, it is K2, direct productive with K3. Here is your K2, here are your K3s. And there is no other Cayley graph of degree 3, regular of degree 3 of order 6. So we found all of them for 6. You can actually, is there another way of choosing generating set with 3 elements? Can you prove that? Quickly prove that. If you choose 1, then you have to choose 5.
Yes.
If you choose 2, you have to choose 4.
Yes.
3 is already there.
Yes.
So this is all. We found all of them. Determined by Z6 and S are obtained exactly once. Each one of them is obtained exactly once. If you are into computational something, you need to really be able to compute, meaning that you can actually construct them. But if you construct the same graph, same object again and again, you are wasting your time. If you didn't find some of the objects which are already there, you didn't find. So you need to, it would be much better to every object is just constructed exactly once. And that is of course not the case in life, because in life we, especially in reality, waste. Human beings waste lots of things. Oh, okay. What is next? Exercise question next. You need to do this. This is one first question today. Determine all Cayley graphs of orders 1, 2, 3, 4, 5 to 9. It's going to be taking, it will take time. But if you work through even up to 7, 6, 7, it will be quite a you. When I was doing it without first visiting online, of course online probably you can't even find all of them. Doing it all on my own, you get great pleasure out of it. Mathematics is to make you happy. It's not, mathematics is not designed to make you go under pressure. So this is what I say. For
Professor, for all generating sets,
huh?
what will be generating sets?
Generating set, you choose all possibilities.
Okay, sir.
1, 2, 3, up to. Oh, there's another example. We'll do later. That's what I'm trying to determine. Before I forget this one, all photographs of orders 1, 2 to 9. With respect to all possible generating sets. For all, for every. Yes, satisfy those three conditions. So, for example, if the order is 9, you can go to 8. The S can have 8 elements in it, starting with 1.
All times we take a cyclic group or also.
All groups. So you would be also going on to online to check what groups are there in these orders.
Okay.
It is there online, but even if you find all the, yes.
Is there any specific result that tells us that as how many telegraphs we can make?
For cyclic. Your question is for every cyclic group, how many
Like
telegraphs?
for example, you take order 6.
Yes,
So
I got 2.
Yes, we got 2.
For degree 3, but for degree 2 and degree, other degrees we didn't do. Degree 5, we're not talking about that one. You need to find all telegraphs. This is only for regular degree 3. Now, your question gives a very interesting question now. How many different telegraphs are there for a given finite group? This is one question. You should write it down. I think it's recording, so it's fine. How many non-isomorphic telegraphs are there for any given finite group? Number one question. Number two question is, also from your comments, I can deduce how many of those telegraphs which you find of that order are from cyclic groups. So from the cyclic group. So that is another, or even weaker condition, how many of them are from abelian groups of that order? I have a question which is probably not answered yet, something like 20 years old, not published. What I said was, as asked myself in my own note was, for a group G of order n, it is almost all of the telegraphs of the groups of order n, almost all of them are obtained from abelian groups. That, if you can prove it, it's going to be a very influential result. I didn't manage to do anything like that, but this question is still in my note. Many years. Tried a bit and didn't succeed, because you have to have some good group theory as well. So this is another thing now, that before I forget and move to the next one. So let G be any group. This is example 2. Any group of order A. Of course, this is a natural number. Even if we're going to take any generating set, we're not going to include the identity. So the largest generating set you're going to take is one less element. Yes. So let S be equal to G, take away identity. Then does this satisfy? Is it a generating set? Yes, it is definitely, because there are elements in that are not identity. So it's inverse. There, multiply, you get 1 on, so every element is obtained. Just one single check. The other one is, first, this is a generating. The second, one is automatically not in it. We took it out. Third is that every element in there, its inverse is there because 1 inverse is 1.
Yes.
So this satisfies all three conditions. Then what do we have? We can automatically say that x equal to x g takeaway identity is isomorphic is equal to complete graph of order n. Complete graph, because every non-identity adjacency is there. So it goes to every vertex. From every vertex to every other vertex, there is an edge. Exactly one edge. So this is complete graph of order n. In particular, now, that's why your question is good. In particular, if we know that on order n there is a unique cyclic group, which means even if we didn't take any other group, but took that unique cyclic group, but we took that generating set, then we got the same graph.
Yes.
So let me write it in the concise way. In particular, for G equal to the cyclic group, we have the same graph. Take away 0. And additive notation. So set, comma, set equals 0. You see, the question I was asking is very meaningful because we are now seeing this happen. For any group, we first produce that. If you take that generator, then you get complete graph. So complete graph, and in particular, if you take that group to be the cyclic group, you get the same graph. Which means that now, here's another definition I forgot here. So now, another definition. If the group is cyclic group, then we call the graph circular graph. If G is cyclic, then X is called circular. Circular graph was originally starting circular matrices. But it is now, it comes out as a Cayley graph of cyclic group. So this also implies that Kn is circular graph, the circular graph. It is a Cayley graph, no problem there, we did it already. But because of this, it is a circular graph as well. You see, this type of subject is extremely beautiful, and it's like we're just reciting poetry. So a good young man or woman should do beautiful mathematics. That is what I would like you to do. Even if it looks easy or difficult, it doesn't matter. This is why we start from Cayley graph. Now we are going to explain after the third concept comes out. The second type of graphs, of course, there are lots of open problems. I didn't write any except verbally presented one of them. I will give verbally a few of them. There are a lot of open problems. Every one of them seems to be difficult and beautiful. One of them I said already, if you have a group of order n, is it true that almost all Cayley graphs of order n can be obtained by Cayley graphs of abelian groups? That's one of the questions. The other question, the famous question, is called R-Schwarz conjecture, not solved yet. R-Schwarz is my uncle. Academic uncle. R-Schwarz conjecture is something like 60 years old now. It says every connected Cayley graph is Hamiltonian. It is open. Of course, by connected means that the first condition is dropped. So if the first condition is there, then it is, in our definition, every Cayley graph is Hamiltonian.
Yeah.
If you solve this one, you are probably going to be instantly famous. There are lots of attempts, people, good people who worked on it. Hamiltonian means it has a spanning circuit. It has a circuit going through all the vertices. A few notes we need to know. Every telegraph is, first of all, it's a regular degree cardinal theories. Observations, remarks. Regular degree is number of elements. There we took S as 3 elements, and degrees are all 3. And not only so, second observation is that these graphs are vertex transitive. You will understand what vertex transitive means, right? Its automorphism group acts transitively on the vertices, on G. What does it mean? If you take any two x, y, and G, there is an automorphism which maps x to. This is easy to prove. Now I think of my other question. Second question is 1, 2, Q3. We did it on Monday. These are all my favorite graphs. Is this telegraph? We need to do this exercise. Yeah, same question, P. Peterson graph P. Is P telegraph? Peterson graph, and those two graphs are both vertex transitive. So the necessary condition for a telegraph is vertex transitive. But if you prove any one of these not tele, then you prove that the converse is not true. Telegraph. You need to justify your answer. Meaning that whatever you say doesn't matter, but you need to prove it. Three questions already. So we move to any comments now at this moment, or questions or comments. Where did we put it? Yes. You can come here and take a picture if you want of the board and share it with the group. Of course, these are in the slides, I think. Except a few questions which I was asking verbally. Of course, those questions you can find from internet. Second concept, called turbulence graph. The reason that I am introducing these families of graphs is that I hope the geometry questions can be solved for some of these. Geometry questions which I'm going to ask in the next batch of slides, next week. And starting from there, we have lots of, I think not lots, only 8 or 9 open problems which I propose. Questions. Maybe they are easy, maybe they are difficult. So we have heard already about Toeplitz operator and operators, Toeplitz matrices and Toeplitz. No, not Toeplitz graphs. Toeplitz graphs arise from Toeplitz matrices. Toeplitz matrices are the matrices of Toeplitz operators that we heard about. I forgot the name of that girl. So, what is a Toeplitz operator or matrix? What is the matrix of a Toeplitz operator? From a finite dimensional vector space to another finite dimensional vector space of the same dimension.
In the diagonal, they have the same.
Yes, so the entries are parallel to the main diagonal are all equal. If you start with 1, it's all 1. If you start with half, it's all half. Yes. Parallel to the main diagonal. So this was the original definition of Turquoise matrix. Turquoise matrix. We need to define matrix nicely. The linear algebra, first linear algebra book which I have seen recently didn't really define matrix so nicely. Of course, matrix has at least 4 or 5 different definitions and meanings. Each of them gives you a meaning. I would, especially in linear algebra, I would like to define it this way. Let me just start graphically first. So let us say we have m rows and n columns. What are these? This is going from 1 to n. This is going from 1 to n, right? So each of these, for example, ij, the ij position, it is just an indication of a position. Row I, column j. And what are we going to put there? We are going to put unique element from something, which means it's a mapping from this object to something. That's what I want to define everything as mapping in mathematics. So let us introduce some, I'll just erase it later. So let m and the natural numbers denote, it is just to not to write the set fully, we denote that natural number sub m, we cut it at m. Starting from the beginning and cut it at m. And another one, this is probably used in somewhere else, not here. Mn, if you assume that m is at most n. In Mn, we start from m and end at n. So we are defining segments of the ordered set of natural numbers. So just giving some short notation for the segments instead of copying this every time. What is a matrix then? A matrix A is a mapping, in my opinion. Mapping which is, and we need to assume that R is a ring. R is a commutative ring with identity element. Commutative ring with 1. So this mapping A is from n sub n cross n sub n, m. These two are. So this matrix is a matrix over commutative ring with identity element R. And this is one of the definitions. This is actually the linear algebra. It is very suitable for linear algebra. And then we can actually say that its ig element of A is A sub ij, we use small one, which is A of ij. Exactly that element marked by A, which into R. So that is exactly the ring element at position ij. So this is a very nice definition, and from this you can actually. So now we are going to use it. So third matrix P.
Yes, sir.
Yes.
Here why we need R is a commutative ring with identity.
That is where we can define matrix addition, multiplication most naturally, and that is the last general thing we can get. If you go slightly further, you can do the matrix multiplication, for example. And of course, everybody in linear algebra defines it's a field. Of course, field is fine. If you have to really put it as ring, so that in your abstract algebra this becomes a major example. The matrix ring is also ring, not non-commutative, but ring with identity.
Yes.
So that is a very nice. The ring is the furthest you can get, the most general. You can't have any. Of course, if you don't want to worry about operations, you can actually put human names on in this position. Let us say that is first row and that is first column, then I put Muhammad's name there, 1, 1 position. But there you have the matrix, but you can't have another matrix, you can't really multiply or add. Maybe you can add by putting, if you add two different people, then you put them together, but fine, but multiplication, what does it mean? Product of the pairs of people and then put them all together, maybe? I don't know, it will be horrible. So I think commutative ring with identity is yes, mathematical generality we get. Social science generality we don't care. Tij. So its elements are small Tij. So such that for every Ij going from 1 to n, this is a square matrix. Ti plus 1, j plus 1 is equal to Tij. This is the definition of a Taylor's matrix. I have to tell you that there are several people in, especially Professor Sheng Bau, who came to see me yesterday. She did lots of papers on Taylor's matrix. Who was our first Dutch student here? She's at it's called Forman Christian College University. There's something next near to here. Okay. I always forget this name. So now this is Taylor's matrix. If you have a Taylor's matrix, for Taylor's matrix, entries are real numbers, originally. Entries are real numbers. If you have a real number, Taylor's matrix over R, can you suggest me a way to get a binary symmetric matrix with main diagonal all zero? There's a way of getting a binary symmetric matrix. There are many ways, but give me one way.
What, Professor?
Yes. Let us consider T, let T be a Taylor's matrix. Whose entries are all from real numbers, it's over real numbers. If you are given such a matrix, can we get, let us not say symmetric, but can we get a binary matrix from it so that main diagonal entries are all zero?
Transformation.
Transformation, but what kind of transformation? I think it's much easier than that. You shouldn't think too much complicated. You have to always low and do simple, and then you get beautiful mathematics. So these are all real numbers. One way, there's a very easy way of getting a binary matrix. How? Just indicate whether it is zero or not. If a real number is non-zero, the negative or positive doesn't matter, we put 1. Otherwise, if it is 0, then we put 0. So indicate. Number 1 is an indicate. Or characteristic. Indicate it. And then you get a binary matrix. Suppose that the Taylor's matrix is over the ring of integers. Over this. Then every entry is an integer. We can also indicate and get a binary matrix. There's also another way of getting a binary matrix. How? If it is integer, then every integer has a parity, or odd or even. If it is odd 1, if it is even 0. So the other way of getting is parity. If T is over, you should really have this kind of small clever things. It will give you lots of good benefits. You will soon find out this will give you lots of benefits. So the parity, if T is over Z, even over finite thing, you can actually either indicate or parity. So now we have suppose that now we are going to jump a little bit. These will be not necessarily symmetric matrices. They will be binary. They will be binary, but not necessarily symmetric. Then what do we have? The Taylor's graph will be directed graph. which is what Professor Shabnam Malik has been studying for many years now. Also the directed techniques. Now, so give me a symmetric binary matrix. I actually wanted to invite one of you to come and write it on the board so that I can work out this graph, which is Turkish graph. But I think anyone can volunteer to give me a, say, 10 by 10 binary symmetric matrix with main diagonal all 0. You can read it out loud for me if you want.